Hello, my name is Manish Gupta. In this video, I'm going to talk about natural language generation methods for query auto-completion systems. So let's get started. Here is the agenda. So we will talk about RNNs with character and word embeddings. We'll talk about LSTMs with subword embeddings. We'll talk about a hierarchical RNN encoder-decoder model. Then we'll talk about next phase prediction problem or next phase prediction with T5 model. And then lastly, I'll talk about a few problems in using NLG for query auto-completion systems. Why NLG for query auto-completion systems, right? So recently, a lot of deep learning models have been proposed for doing very effective natural language generation. NLG systems have been popularly used for several applications, like for summarization to generate abstractive summaries, for question answering, for question generation, machine translation, and many other interesting tasks. So in query auto-completion systems, typically people show prefix matching suggestions which have been previously queried for by search engine users. However, when such prefixes get too long, for example, this kind of prefix, how to get from San Francisco to LA by, typically the try does not have enough suggestions to show in a suggestion block, right? So, and there are many other kind of examples that you see here. For example, director of Netflix series person of, right? How can I replace battery for, and so on, right? So in such cases, to improve on the recall for such tail prefixes, NLG helps. And that is why people use natural language generation these days for query auto-completion systems. There are several technical challenges in developing such systems. For example, when you look at prefixes, these prefixes may or may not end at a subword boundary. Right? In those cases, how do you handle partial words in the input? Optimization of computational requirements and throughput. So Autosuggest is a system which is supposed to be a very high throughput system. So then how do you ensure that these deep learning models which you deploy can lead to very low latency and are super optimized? Right? So model compression distillation, you also want these models to be small in size so that several instances of them can be run on the same machine with limited RAM. Typically, for natural language generation using deep learning, people use beam search for better generation. However, in the case of autosuggest, latency is a primary concern, and therefore you can not use beam search. You have to leverage greedy decoding and still be able to come up with really good suggestions. There are several considerations when deploying NLG models for query auto-completion. For example, you need multilingual support. You need to ensure that if the user has typed in a French prefix, you come up with a French completion. You should not show like a Spanish completion for sure. Inappropriate leakage, you have to ensure that nothing inappropriate comes up. Suggestion quality, you have to ensure that the quality is reasonable. You don't come up with very poor intents or rare intents. You don't come up with partially complete suggestions. All of that quality needs to be controlled. Coverage. So NLG is supposed to bring in good coverage, especially for tail prefixes. So, and that is the goal that you have to keep in mind while designing NLG mechanisms for QAC. Latency. Clearly, whatever you are doing, you have to ensure that you can show the suggestions within, let's say, 100 millisecond budget. So before proposing deep learning based solutions for NLG in QAC, people have come up with non-deep learning methods as well. So one of the most popular non-deep learning methods is Query Blazer. This was very recently proposed, and this method is based on finite state transducers. So during training time, it first learns a subword vocabulary, which can be used so as to build a finite state transducer with those vocabulary subwords as states. Um, using a very large query log and this subword level vocabulary, this particular model, the Query Blazer model, essentially learns a Query Blazer methodology learns a subword level language model. At test time, essentially you use this subword level finite state transducer to take in a query prefix and then figure out most probable completions and suggest those top k completions to users. So now let's start with talking about deep learning based models for natural language generation to be used in query auto-completion systems. Let's start with basic models which involve character or word level RNNs, and then slowly move towards more complex models like LSTMs, hierarchical RNNs, transformer-based models, and then lastly talk about some problems with these natural language generation systems. So one of the first few systems for natural language generation for QSC involved character level language modeling. Clearly, compared to word level language modeling, character level models are capable of handling out of vocabulary words. They can use the last incomplete word also, which is a part of the prefix, so as to generate the completion. As you can see, these kinds of models can actually generate very awesome completions. When is a good time to buy a house, home, car? Now, of course, some of the suggestions are not so good. Lyrics, who buys? I mean, it's a good time to buy lyrics? No. But most of the suggestions are reasonably good. The model is a pretty simple model. It basically uses LSTM layers, multiple layers of LSTM, and finally, of course, the softmax layer. It's a next character prediction system in some ways trained on large amounts of query logs. Rather than just using character embedding, they essentially use the input is divided into three parts. One is one hot encoding of the character. Next, there is a character embedding. The blue cells contain character embedding vectors. And then there are these red things, which are basically word embedding vectors. Now, for characters which correspond to anywhere in the middle of the word, you basically use a special word called incomplete INC token. But for characters which indicate the end of the word, for example, space in this particular word, you use the embedding for the particular word precedent in this case as the word to be embedded. People have compared these neural language models with many other previously proposed models. For example, the most popular way of coming up with suggestions in QA systems is MPC, most popular completion. People have also used character engram so as to come up with completions, like typical character language engram models. Folks have also used models where given a set of popular suffixes, you just want to check which of these suffixes is most compatible with the user type prefix using a deep learning way, and then combine it with most popular completion using a lambda mart model. Uh, Several other baseline models have also been tried. For example, there is this NQLM model, which is basically the same language model, not using word embedded character space. So essentially, NQLM model just does not make use of these red colored cells. There are also NQLM plus WE, which is sort of ablations of the proposed model, which uses word embeddings and so on. So what people have observed is that typically you get way better results using this proposed character RNN-based model, which basically makes use of not just the word embedding, but also character embeddings, both one hot as well as distributionally encoded character embeddings. It also makes use of most popular completion as an additional feature and combines all of it together using the lambda mart model. The measurements were done using two metrics, MRR and PMRR. MRR is mean reciprocal rank, and it's a pretty standard metric. Partial MRR was something that these guys coded up. So the partial MRR, the idea is partial MRR rank is always going to be less than full MRR rank. The way this is done is to incorporate partial matches. So a character level neural language model is not expected to generate full and complete suggestions. So even if it could generate a partially okay suggestion, you would still give it brownie points. So that's the broad definition of PMRR. And they observed that on PMRR, their full model gives reasonably good results for both seen as well as unseen parts of the test data. It specifically works really well on the unseen part. And this is the part where trie-based models are going to give you absolutely zero MRR or PMRR because there's nothing in the trie, right? So you can't suggest anything in no most popular completion method works there. And this is where the natural language models add a significant. Next, let me talk about LSTMs with subword embeddings. So character embeddings were great. However, representing queries with subwords shortens the decoding length significantly. Character-based language models take a lot of time because you are decoding character by character, while subword level language models decode subword by subword and therefore are faster. However, subword level language models have their own problems to deal with, specifically the following. If we segment the prefix as given, to encode it using neural networks, the segmentation of the prefix may not match with that of the ground truth query because the prefix is an incomplete substring of the original desired query. Right? So the subword level boundary that you get when you try to segment the prefix may be different from the subword boundaries that you may get if you were segmenting the original query. This basically means the following, that the enforced segmentation is less likely to appear in training, and the model starting from this segmentation is going to be unlikely to reach to the ground truth original query, ground truth query. And therefore, people have sort of experimented with two different kinds of such segmentations of prefix. One is the byte pair encoding algorithm, which is deterministic because it segments greedily from left to right. So that's one way of doing things. The second one is called subword regularization, which samples multiple possible segmentations by utilizing a unigram language model, as we will see on the next slide. So in subword regularization, the idea is that let's say you have a ground truth query restaurants, right? And essentially, this is how the ground truth subword segmentation happens. Rest, or these four different subwords, right? However, if the user has just typed in res, right, the subword segmentation basically gives you two subwords, re and s, which is unlikely to lead to the entire query restaurants because at res itself it just doesn't match with the subword boundary of the original ground truth. So subword regularization basically says that, hey, look at all possible segmentations and then try to take, marginalize over all of them. But that is basically intractable. And remember, we have stringent latency budgets for query autocompletion. Hence, the idea is to essentially use something called as the retrace algorithm. So what does the retrace algorithm do? Well, you basically go a few characters back from the end and generate candidates with the restriction that they should match with the retraced characters. Okay. So the idea is that you get the segmentation as follows. So res is what the user has typed. So fine, get the segmentation of res and then try to generate the next few things. The second option is to basically go back one character and take RE and then do segmentation. In this case, RE is a token by itself. Then you generate, things, and then you take only those generations which match with S as the first token. Further, you can remove R, you can just have R and then call it as a segment and then generate all possible next things. But then you take only those tokens which start with ES. And lastly, you can basically imagine that, hey, whatever was before restaurants is the total prefix, and then you start generating the next token. And if it starts with res, you keep it, else you don't keep those tokens. Okay? So that's basically one way of sort of leveraging the subword level language model for QSE by handling this subword boundary mismatch problem using the retrace algorithm. People have observed that subword level language model is 2.5x faster compared to a character level language model. This paper also introduced an interesting metric called as mean recoverable length. So in this metric, the idea is to measure how many upcoming characters the model could could complete correctly, right? So the idea is not to care about ranking. So they do not really focus on the ranking order of candidates, but they just look for how much of the completion was possible thanks to these subword level language models, and thereby how many keystrokes of the user was saved in some ways. Okay, so those were RNN and LSTM based models. Now let's talk about the popular HRED model, which is hierarchical RNN encoder-decoder model. So this model treats the natural language generation for QSE problem as a hierarchical problem. So here the input is the user session S, And it is supposed to be built out of queries, and queries are supposed to be built out of words. That is where the hierarchy comes in, the two-level hierarchy comes in. Right? So accordingly, this is modeled using a two-level RNN. The lower level RNN tries to model the words in a query so as to come up with a representation for the query, while the higher level RNN essentially tries to take the embeddings for each query and come up with a representation for the entire session. Further, once you have encoded the existing session queries and the current prefix using a hierarchical recurrent encoder, you would then follow it up with a decoder which generates synthetic suggestions sampled one word at a time. So it generates one word, next word, third word, and so on. Of course, it's going to be really, really useful for tail or long tail kind of queries. Okay, so you could of course combine the HRED score with the other features in the Lambda Mart model, and the people have shown across different kinds of test scenarios that this leads to significantly awesome results. So as you see, if the user session was a series drive, these are the synthetic suggestions which are very relevant to what the user was searching for. So in some ways, it sort of also brings in a notion of personalization with respect to the current session, or contextualization with respect to the current session. So the user had typed in these two queries, Cleveland Gallery and Lake Erie Art. The suggestions to make a lot of sense: Cleveland Indian Art, Lake Erie Art Gallery, Lake Erie Picture Gallery, and so on. So in this specific paper, these folks combined the HRED score with a baseline ranker, which contained 17 different features, pairwise features, suggestion features, contextual features, and so on, and showed that they get really good results when they combine, when they augment the baseline of 17 features with their HRED score, which is the log likelihood of the suggestion given the context using this hierarchical encoder-decoder model. The model was validated across three different test scenarios. Um, the test data for these three scenarios was created in different ways, and three scenarios sort of vary in terms of complexity of the test set. So the first test set is pretty simple. You essentially take a particular query, you take a session and you take the last query, and then you take the next query, which was you extract 20 different candidate queries that most likely follow the anchor query. Okay, so look at a lot of session data, and based on session co-occurrence data, you try to check which query will come up as the most popular query. And then if the clicked query is among 20 most popular queries, you consider that as a test instance. Okay, so it's a very simple test set. I mean, not very difficult. The second one is the robust prediction test set. Here, the test set is created in a very similar way as the first scenario, except that you add noise in the session data. So now, what do you mean by noise? Well, you add a noisy query in the session data. So you find 100 most frequent queries in your query logs, and then you take the same kind of test set as you created in test scenario one, and then at a random place in your session, you essentially ingest or introduce this noisy query selected randomly from these top most frequent 100 queries. For example, if your session was airlines, United Airlines, and now you're generating the next query, you would rather the target is Delta Airlines, then the corrupted instance would look like this: Airlines, United Airlines, Google. Now, Google is one of those noisy queries which has been introduced as an extra noise in the input, right? And then you try to predict Delta Airlines still. That's a little more complex than test scenario one. Test scenario three is even more complex. It's useful for long tail prediction. So the idea here is that you retain the sessions for which the anchor query has not been seen in your entire query log or the background set for so the anchor query is unseen. That's the point, right? So then how do you basically figure out the candidates and the target? Well, for each session, you are going to iteratively shorten this anchor query, which is unseen, until you have seen it in the background set. For that, you will take 20 different candidates, which most likely co-occur or follow this shortened query across existing sessions. Now, if the target is present in those 20, you take that as a test instance in the test scenario 3. So test scenario 3 is about unseen anchor queries, right? So that's basically what it is about, and therefore it is much more complex than test scenario 1 and 2. The HRED folks actually compare their method with two other baseline methods, ADJ and baseline ranker. So ADJ is adjacency based, session co-occurrence based method. So what particular queries are most frequent, what particular query Q2 most frequently co-occurs after query Q1. And what they observe is that across all the three test scenarios, the method leads to significant improvements on top of these baselines. A very interesting observation, though, in the paper is the following. If you look at the human evaluation of HRED outputs, you observe that about 37% of these are actually useful. And that's the great observation because a lot of the outputs, even coming from their system, are not very useful. Now, even though the natural language generation systems in deep learning have made a significant progress, right? Even in 2015, they had made some progress. The progress was not enough to make these systems practically possible just because of this large gap, right? So although the system is so nice, it is nice theoretically, right? There are a whole bunch of not useful suggestions coming up and a whole bunch of somewhat useful suggestions. It took quite some time. It took quite a few years from 2015 to make these systems practically usable. But in 2015, people did show that there is value. There are at least a large bucket of suggestions which are useful, which are being recommended by HRED. Next, let's talk about this system called as RIN, Reformulation Inference Network. So the idea behind this system is to actually first build an inference network, a network which has terms, queries, and websites as nodes. Okay. So terms are just words. So baseball, sport, matches, basketball, exciting. Queries are queries. So past queries. So for example, baseball matches is a query, exciting baseball matches another query, and so on. And then there are websites. Right? So there are four kinds of edges in this graph. Uh, Words are connected, terms are connected to each other because they're consecutive terms in some query. Like baseball matches is a query, and matches is followed by baseball is followed by matches, and therefore there's this edge right there. There are also consecutive queries across sessions, and that is what forms links between two queries in this graph. Query term relations basically show the containment relation. So baseball matches contains the keyword baseball. There are similarly exciting baseball matches contains the keyword exciting and so on. And then there is click-through information. So queries are linked to websites because they lead to clicks to those websites. The idea is that given this graph, one could use popular graph neural network-based methods so as to come up with an embedding for each of those nodes. So in their particular case, they use a method called as node2vec so as to come up with an embedding for each term, each query, each website. Now, given these embeddings for queries, you could look at two consecutive queries in any session and then call the difference between the embedding vectors for those two queries as reformulation. So what is the reformulation? Well, reformulation is the difference between embeddings of the queries at the ith plus one time minus minus the embedding for the query at the ith time. Okay. Now, how do they use this kind of query embedding that they have learned for query suggestion? They build this context-aware query suggestion network so as to be able to do so. Okay. There is a query session encoder, which is basically an RNN. The way it encodes things is as follows. More specifically, it's an attention-based GRU. Right? It's an attention-based GRU encoder-decoder network. You see, this part is the session encoder, GRU-based session encoder. This part is the decoder, the GRU-based decoder. Okay. As you see, the queries in the session have been encoded using the homomorphic query embedding, which is basically the node2vec embedding from the graph we discussed on the previous slide. You also see that there are these reformulation vectors, right? And they have been obtained for the previous queries in the session as differences between query embeddings. Now, these reformulation vectors, along with query embeddings, are fed as input to these hidden layers in the GRU. Further, a query session, this query session encoder also has this query session attention layer, which is basically used to supply encoder-decoder attention to our query generator, the decoder part of the encoder-decoder model. Right? In fact, the decoder side has three parts. One is a query generator, which is a traditional decoder of a typical GRU encoder-decoder framework, but they also have a reformulation inferencer, which essentially uses this context vector coming out from the query session attention so as to infer what will be the reformulation when generating the next query. So you have the current query, the Lth query, and you want to generate the L+1th query. What will be the reformulation involved, right? So it's sort of trying to learn the difference vector. Also, what you see is the discriminator. So this particular discriminator is trying to say that, hey, if I have a particular query candidate, what is the probability that if I give this context and this query candidate, that there'll be a click on that query candidate, right? So it's sort of a click predictor. Thus, our decoder part actually has three parts, right? A decoder has three parts: reformulation inferencer, query discriminator, and query generator. The reformulation inferencer tries to predict the next reformulation. The query discriminator tries to predict what is the probability that Q candidate is the intended query. And the query generator, of course, tries to generate the next query, right? So, and it does this generation by making use of the context vector, which has been obtained by learning the attention weights in the encoder-decoder kind of a framework. Okay, so that's RIN. Now, of course, since there are three different parts to the decoder, all those parts are essentially used for optimizing the overall loss, right? So overall loss. So there is a discriminator loss, there is a generator loss, and there is also a reformulation generator or a reformulation inferencer loss. These folks actually compared this RIN model with several other baseline models. As you see, they have been compared with several other baseline models and other models that we have talked about so far. Many of them are things that we've already talked about. Like just before this, I talked about HRED. They're compared with HRED as well. In a previous video, I talked about ACG, Attend Copy Generate model. They compared with that as well. They have, of course, compared with the most popular suggestion or the most popular completion baseline. And they have compared with the Markov models, the query-based variable Markov model. They've also compared with with reformulation-based completions. So just use reformulation. In one of the previous videos, I talked about 43 different reformulation-based features in a table. So they compared with that reformulation-based Lambda-Mart learning to rank model also. And this comparison has been done across sessions of different sizes. So sessions which had one query in the context, which had 2 to 3 queries in the context, or 4+ queries in the context. An interesting observation is that their model, of course, does better across all of these buckets. In fact, it does work really well when the sessions are shorter in nature. Now, it is sort of obvious when the sessions get a longer, the accuracy drops a little bit because it becomes a little difficult to make use of the noisy session information. Okay? But then it works really well when you consider sessions of shorter size. Okay, so now we will talk about next phase prediction with T5. Transformer-based models became very popular in the entire of NLP starting from 2018. In 2021, folks came up with this interesting model where they've used the T5 model so as to come up with the next phrase, predict the next phrase. And this particular work was not on web search, but query autocompletion for emails or for academic writings. Right? The idea is that you could use a traditional GPT-2 model so as to come up with the next phrase prediction. And if you do so, GPT can actually generate some reasonably good suggestions. So you see, these are suggestions generated by GPT. The approach for organizing the computation of the values is identical for two types, right? Or a reservoir is usually a recurrent neural activity or the activity of an associated memory. So GPT suggestions are reasonable, syntactically sound, but semantically general sentence, but they are semantically too general. They are not really very specific or more clear, or more obvious intent is not being shown by the GPT-2 model. However, we need to, if we want to just use GPT model, we need to fine tune it a lot to generate semantically, domain-oriented generations. Okay. So, for example, in a computer science domain, the approach for organizing the computation should lead to things like process on the GPU is described and so on. So therefore, what these guys did was to train a next phrase prediction model using the popular T5. Okay. This next phrase prediction loss function sort of motivates the language model to complete the partial query with enriched phrases, with phrases which are more domain specific and which are rich in nature compared to very generic bland phrases. Okay. The way it is learned is in two steps. One, phrase extraction, and second, generative question answering in some ways. Okay. Then, of course, there is a third phase of essentially fine-tuning it on query autocomplete data, right? But the first two important phases are about further tuning this T5 model to become aware about generating rich phrases, rich next phrases. Okay? The way this is done is as follows. Phrase extraction is done using constituency parsing. So you could basically run a constituency parser, let's say from Stanford Core NLP, and extract phrases, constituency parses of this kind. This is called a constituency parse for a sentence of this kind. The sentence is she bought a top and bottom from the strange little shop. The constituency parse essentially divides a sentence or builds a tree structure, syntactic tree structure over the entire sentence. Okay. The lowest layer is essentially part of speech tags, and then these words are sort of combined in form of phrases at different levels. Okay. So here is a noun phrase, here is a prepositional phrase, here is another noun phrase, verb phrase, and at the top, of course, the root node called the sentence. Yeah. So as we see in this sentence, there are two noun phrases, a top and bottom, sorry, right? And then that strange little shop, two noun phrases. Yeah. So the way that this particular T5 model is going to be trained is for generative question answering, where the idea is to provide this as the input, generate next phrase she bought, and then give two options, A or B, a top and bottom, that strange little shop. And then of course, the obvious answer is a top and bottom, okay, and not that. So she bought that strange little shop doesn't make sense. So she bought a top and a bottom. Okay, so that's that. So the idea is to basically guide the pre-trained language model of the T5 to choose the correct next phrase among other phrases of the same type. So remember, if the next phrase is a noun phrase, then you would consider all of the noun phrases from the same sentence and ask it to choose the correct noun phrase, the right noun phrase, which should follow right after this string rather than the wrong one. Okay? So they trained the T5 model with this next phrase prediction kind of an objective as against the next sentence prediction objective, and across a whole bunch of natural language generation metrics and on two different data sets, emails and academic writing. They observed that compared to the vanilla GPT-2 or T5, their model gives way better results. Okay. Here are some examples from their model. So this is the partial query. There are 4 columns here, the partial query, and you want to complete this. So this is the original completion. This is a completion, the vanilla or the bland completions that you get from T5. You see, challenging, system, et al, and so on. Very, very simple, short completions. But next phrase prediction tuned or model trained on this next phrase prediction loss gives you way better results. Results which are very, very comparable to the original completions that were there in the data set. So that's next phase prediction using T5. Next, let me talk about problems with natural language generation systems. Natural language generation systems have been hailed as very interesting systems capable of handling the recall problem in query autocompletion. And they do this job really awesomely well in many cases. For example, for the query should I, it leads to nice completions like learn to swim, should I buy a car, should I cut my hair, that's okay, should I get a pet, that's okay. But what is not okay is should I quit my job, right? Should I end my life? Really? I mean, so some of those generated suggestions could be nasty, very nasty. And the goal is that you should be somehow able to handle these problematic suggestions. So therefore, whenever you're using natural language suggestion generation for QAC systems, you have to be very, very careful about different kinds of nasty generations, right? Here is another example. Depression is a choice. Depression is just for losers. Too bad, right? I mean, you cannot have energy system generate such nasty suggestions. Generated suggestions could be racist, sexist, may contain violence, and so on. And, sometimes they could have subtle hate. For example, you look at this, in general, a suggestion that contains is evil or is huge may be acceptable. But if the user input was heinous crime, clearly is evil is not acceptable, right? or or the universe is evil. No, not acceptable, right? So uh, 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 sorry, so I mean these are acceptable, if the user input was heinous crime is evil is okay. But then, if some person's name was there, right? So Manish Gupta is evil is not okay, right? So therefore a simple usage of blacklist is not going to help here, right? So, therefore, there needs to be some more thought put into how to handle such problematic suggestions. In fact, people observed that 15 to 20, 47% of problematic suggestions were flagged as problematic due to the query prefix that they were surfaced for. Sometimes the query prefixes are themselves nasty, but then the idea is that query prefixes are input by the users. They can type whatever they like. The systems have to be careful so as to still avoid generating problematic suggestions. Many times problematic suggestions are generated for search voids. Search voids are rare query prefixes. Um, and in such cases, problematic suggestions were 3x more than problematic suggestions in other cases. Problematic suggestions can also affect the dignity of people who are searching, the users themselves. So, for example, suggesting bed bugs by yourself for the prefix how to kill bed bugs by yourself is sort of suggesting that the user in themselves have a bed bugs problem. Or if the prefix was how to find, and then if you suggest my arrest records, you're sort of suggesting that the user has some arrest records and so on, which is too bad, right? In fact, a whole bunch of problematic suggestions can be possibly generated by such models. There are several such problem categories, as has been discussed in detail in this interesting paper, right? So there could be harmful speech generated. For example, uh, which poison can kill an adult fast? So the prefix is which poison can kill. Of course, the prefix itself is nasty in some cases, right? Should I punch? Nasty prefix. But then, you complete it by my mother. That's even nastier. Or sometimes, the prefix is nice and fine. Should woman be? But then you complete it by hit by man, right? So that's basically leading to violence and so on. So, so therefore, sometimes the prefixes themselves could be nasty. Sometimes the suggestions, the suffixes that are generated could be nasty. Uh, and there are different kinds of problems. So potentially illicit suggestions like trustworthy website to buy heroin, really, right? Or how to get fake passports and so on. Sometimes there could be controversial suggestions generated, misinformative ones, stereotypes, bias, adult queries, other types of suggestions like animal cruelty, so how to strangle a dog, or and so on and so on. Right? So one has to be extra careful about using NLG systems for QSC. The suggestions could be problematic and targeted towards different categories of things or users, right? So they could be targeted towards individuals. So for a particular person name, if you're generating dead yet as a suggestion, that's too bad, right? Or it could be targeted towards some groups, like Muslims or children and so on, or targeted towards some businesses or organizations. Uh, in bad suggestions, problematic suggestions could also be targeted toward animals or objects, like how to poison a cat, right? Or they could be also targeted towards certain kinds of users, like bipolar disorder patients, that's fraud or vaccination herd mentality, and so on. So there could be several targets of these these problematic suggestions. In short, the idea is that yes, if you are using NLG for your QAC system, be very careful and mindful of generating a of coming up with a very strong mechanism to deal with such bad energy generations. There is recently some work which tries to avoid such toxic generations. So, for example, there's a model called as T-Experts, which basically tries to learn a language model such that it generates things which are non-toxic in nature, or it promotes generation of words and completions which are non-toxic in nature, but but avoids toxic generations. Right? So, however, there is more work to be done in this area clearly. To summarize, in this video, we talked about energy mechanisms for query autocompletion. Specifically, I talked about RNNs with character and word embeddings, LSTMs with subword embeddings. We talked about hierarchical RNN encoder-decoder model. We talked about transformer-based models like T5 and next phase prediction kind of pre-training for it. And lastly, we also talked about problems with deploying such natural language generation kind of methods for query autocompletion. Thank you for watching. Hope you liked it. Connect with me on LinkedIn or have a look at my research work on the homepage. Thank you.